Good afternoon, I am Mr. Ish. You are joining me for this video. Additional practice on these volumes and curves, looking at something slightly more difficult than the norm. We have here a single question for this video and it should be a good one. Y equals secant square x, y equals 2, and rotation around the x-axis. This will be a good revolutionary solid and I will show you after we've done the graph. If you're looking at the graph of y equals secant square x, you can always look at it in terms of a software, graphing software. You'll notice right here from 0, 1, let's just put the point right here, 0, 1. You have something which goes upwards right here. You have a vertical asymptote as you normally see with the secant function at pi over 2 minus and positive pi over 2. You know, normally a cosine graph would come right here up to this and then it would go downwards into its serpentine manner. This right here is secant square x. When we're looking at y equals 2, if this is 0, 1, a good representation of y equals 2 can very well be this. So you're looking at the region between this curve, these two curves. You know, there's a top boundary curve which is y equals 2 and a lower boundary curve which is secant square x. If you're rotating it right here on the x-axis, you know you're going to have a similar image. Well, let's just say we'll have a similar image developed right over here. And you know, a three-dimensional nature of a solid will develop and you have this region in between. The solid will look interesting. It would be something like this on the top and something like this on the bottom. You have this region in between which is enclosed by these two curves, and then you have a three-dimensional nature to this which comes out like this. And we can give it like a little bit of a diagram over here, though the diagram is failing here because my art skills are weak. But this right here, you see this y equals 0 line, my x-axis, that right there is this line which is coming through. And you know it's a revolutionary solid. There's no point over here which is fixed like a spinning point on a surface. Everything is revolving in a translation. So this right here is a solid of revolution, a true solid of revolution. Anyhow, we're not focusing here too much on these diagrams over here, but we are focusing on the technique. You know, you have to determine some points over here, this intersection point, because if we are looking here with the horizontal line of axis, right, which we are, you know, volume will be in regards to x. You'll have a and b intervals along the x-axis. You'll have some sort of outer area minus inner area with regards to dx. Why do we have outer area and inner area? Because we have a washer cross section. If you were to slice this through right over here and look at it, in all aspects you'll have a washer develop, and you know that will give rise to inner and outer area. Again, this right here is my x-axis, y equals 0. From here to this line right here is my inner radius. From this x-axis going up to this, that's my outer radius. What exactly is this line right here? The tip of the secant square function. That's your lower edge. What's this upper edge? That right there is my y equals 2 line. So you have clear inner and outer radii to deal with, and we need to do some good intersection points for interval development. We don't know what our intervals are. Intervals are not minus pi over 2, pi over 2. The intervals are something else, and we have to determine that. And we can do that easily, and I'll show you how we will do that. The intervals are developed easily by making these two equal each other. Secant square x is equal to 2. Take the square on the other side. Secant x is equal to plus and minus root 2. Secant x is also equal to the reciprocal of the cosine x, right? Flip the cosine x up and flip this down, and if you remember your trigonometric radians and your degrees, this right here is plus and minus pi over 4. If however you did not remember that, you can easily do this on a calculator. You can do 1 divided by root of 2 inverse cosine and you get a 45 degrees. But cosine and secant are both even functions, symmetric about the y-axis. So if there's a positive pi over 4, then there must be a minus pi over 4. Your intersection points are minus pi over 4 comma 2 and then positive pi over 4 comma 2, and these right here are your intervals. You can look at your a and b intervals for the integral. So everything is beginning to fall in place. Let's set up our integral over here. What is the integral for this volume? Volume with regards to x is equal to, we have a minus pi over 4 and a positive pi over 4. Let's do our inner and outer radii. From here, my line of axis always up. Here's my inner radius. From my line of axis going up to the next curve is my outer radius. My inner radius over here is from x-axis to this secant function, right? Secant square x. My outer radius is from the y equals 0 x-axis up to that horizontal line 2. Area inner will be what? This pi r square, because everything here in terms of slice is a circle having area pi r square. So this becomes pi secant 4x. Remember, secant square x squares is secant 4x. Area outer is going to be a 4 pi. This here will create a little bit of a challenge in terms of integration, but we'll solve that before we do it. Anyhow, outer area minus inner area with the pi's pushed out, isolated and pushed out, we have a 4 minus secant 4x dx. That right there is my integral expression for this entire volume solid that would develop. So what we have to do now is solve that secant to the 4x, and I'll show you. At some point in this integral process, this will come into play and it will be an issue. And how would you on the side determine the integral or the antiderivative of secant to the 4x? Let's just do that, and we will save everything here on the side. This right here is my problem. Secant square x is also equal to tan square x plus 1 dx. Separate everything across this positive sign. You'll have a secant square x tan square x dx plus secant square x dx. What did I do? I multiplied this with this, and I multiplied that with that, and I separated across that positive. Polynomial substitution technique. If u is equal to tan x, then du is equal to secant square x dx, and dx is equal to du over secant square x. This becomes easy. Secant square x u square du over secant square x plus this right here is a clear antiderivative, which is just tan x, because the derivative of tan x is secant square x. Therefore the antiderivative of secant square x in terms of integral must be tan x. We are so close to solving this. This is polynomial now. It's u cube over 3 plus tan x. But look, when we bring this into picture right here, since we did all of this, new intervals will come into play. So let's even look at that. Let's do a little modification over here. Even intervals, 0 to pi over 4, same thing as looking at from minus pi over 4 to pi over 4, but you multiply everything by 2, and we know that's a property of interval for an even function. We know this, we can do this. Now let's come back over here. This was really from 0 pi over 4 with a 2. But we're focusing only on the intervals. Up to this point right over here, I had a 0, I had a pi over 4. Here I had a 0 and I had a pi over 4. So now we have to remember what comes into play. The secant to the 4x will give me an antiderivative of u cube over 3 plus tan x. This will have some interval pi over 4 over 0, and there's a 2 outside which we won't forget because I have it placed here. U cube will bring me another interval. Why will it bring me another interval? Because of this part right here. When I started doing u substitutions, intervals changed, u1 and u2. Everything was with relation to this. U is equal to tan x with regards to 0. u1 must be tan of 0, which is 0. u2 must be tan of pi over 4, which is 1. So when we do this, we will have a lower interval limit of a 0 and upper interval limit of 1. If you are falling out of track over here simply because I've done too much, keep in mind I solved this separately because this is kind of difficult and it would be a nuisance to deal with when we're doing the volume. I brought this over here and I separated it out. I also had a minus pi over 4 to a pi over 4 interval to begin with, which using the properties of even functions, I made 0 to pi over 4 by added a 2 because you can do that. I've talked about that many times and you can do that. This 0 to pi over 4, what plays around over here, you know, here with the separation across the positive sign, the 0 to pi over 4 didn't get affected because no substitution came into play over here. But the 0 and the pi over 4 got affected over here because we did a polynomial substitution technique. The 0 became a tan of a 0, which is a 0, that's a u1 value, and then the u2 value, the upper limit for the interval in terms of u became tan of pi over 4, and that's a 1. So I've saved all of this for the part which will come into play over here. We have now everything we need to finish this volume determination. I have the main part right over here. When we come back over here, we separate everything across the minus sign. I have a 2 pi and then I have a pi over 4, 0, 4 dx minus. See that minus? Then 2 pi and then I have a pi over 4, 0 secant to the 4x dx. It's not hard because I have all of this in play over here. This 4 can be brought outside and becomes an 8 pi from a 0 pi over 4 dx minus. Let's do 2 pi. And we don't need to put this integral sign anymore because we already integrated with that elaborate procedure, which was equal to u cube over 3. This is from 1 and 0, right? I've already done the integration, so why will I create a new integral process of something that's already been integrated? Now we just have to do the definite integration. Plus tan x, and this here is from pi over 4, 0. This is easy. This comes out as an x, 8 pi over 4, 0 minus 2 pi. Let's solve this out. You're putting an upper limit 1 and a 0. 1 cube, 0 cube, difference of the two is just a 1 over 3. Tan of pi over 4, tan of 0 is 0. This is just a 1 right here. This here is 8 pi times pi over 4. 0 is meaningless. Minus 2 pi times 4 over 3. This all is equal to the volume of the solid we've been looking at. Here I get a 4 going to 8 2 times. I get a 2 pi square. Here I get an 8 pi over 3. You can do a numerical value of this. This right here is a good volume right here answer. 2 pi square minus 8 pi over 3. But we can do a volume determination here in terms of a good numerical value. And I get a volume determination out here of 11.362 units cube. Because we're talking about volumes, we'll do cube, but units is an arbitrary unit here. Again, we looked at the volume determination of some solid which came out to be a true revolutionary solid having the appearance such as this. Alright, like that. It happened to have this area, which is the region between the secant square and the y equals 2, and of course the mirror image. And then you can give it a little bit of a three-dimensional nature over here. You have this coming out as my line of axis, which is y equals 0. But that right there, it was my rotational solid. Through and through open, with some sort of this convexity coming in and filling in a good portion of the space as it revolves around. But it would be through and through open, and you would have a good inner and outer radii develop in this as you saw it. But this right here is the solid which developed, and we examined that in this video, and the volume is right over here. Volume with respect to x. And with that we conclude this video. Thank you for watching. Have a nice day.